Good afternoon, everyone. I am Steph Nelson, your host. I'm an application engineer at Siemens. Your presenter, who will be talking about what's new in Test Lab with virtual prototype assembly and vehicle synthesis, is Scott McDonald. All right, Scott, I'll turn it over to you.
Thanks, Steph. Well, as Steph said, we're going to talk about virtual prototype assembly and a new option that you may have seen if you've installed version 2406. There is a new add-in available in Test Lab Neo called NVH Simulator Offline, and we're going to talk about that as well. But to start, just to give some perspective on virtual prototype assembly and what it's really about, it all has to do with streamlining and making more efficient and cost-effective the vehicle development or product development cycle. It certainly is not restricted to the automotive industry. It's certainly a big area of application, but it's applicable to any device or machine that has prototypes that are built and tested, and then maybe modifications are made to throughout the development process in order to solve noise and vibration problems. In the auto industry, this study done by Automotive Testing Technology International found that the cost of a prototype can range anywhere from $250,000 for a development mule vehicle, as they're called, which is starting with an existing product and cobbling some changes onto it to represent in some crude way the new generation. You're starting with existing stuff, and so it's not quite as expensive. But by the end, when you're building your final prototypes, those can be up to $1 million per prototype. And typical vehicle programs have historically used 50 to 70 of these vehicle prototypes over several stages, so you can imagine the amount of money. What it results in is a lot of organizations are thinking about how can we reduce or even eliminate physical prototypes from our development process. We want to better leverage the test resources we have, better leverage the CAE or simulation resources we have, and make better decisions earlier in the product development process. That's the question that VPA, Virtual Prototype Assembly, is really trying to answer. One of the enabling tools or underlying technologies here is this thing called component-based transfer path analysis. If you've been around noise and vibration for a while, you've probably heard of transfer path analysis, which is a very popular problem root causing technique you can use to figure out how is the energy, noise or vibration, getting from our source, whatever we're considering our source, to our receiver, usually a human being, either a microphone response or a vibration that we'd measure with an accelerometer. How is the energy getting from one place to the other? And so how can we best address and lower the noise or the vibration at the receiver location? An extension to that is this component-based transfer path analysis, where instead of characterizing the entire system with source and paths and receiver, we're really characterizing individual components. So individual sources. In this slide here, we're showing a tire wheel combination as being the source. In this case, it's for a road noise CTPA investigation. And so the tire and wheel is considered the source, and we pull that off the vehicle or out of the assembly, and we just characterize that source. Then we have the suspension and body combination, and we consider that to be a single component, and we characterize that individually. Okay, so now we're not characterizing them as a system, but rather individually. What that allows us to do is now virtually assemble any number of tire wheel combinations that we have characterized independently and install them virtually on any suspension body combinations that we have also characterized independently. And so we never have to have the actual wheel and tire, and we never actually have to have the actual suspension and body to physically put them together. We can do this using mathematics and some techniques like frequency-based substructuring. It allows us to predict what will the response be at the driver's ear or the steering wheel vibration given that we put on this tire and wheel combination. Okay, so that's the idea. We'd love to be able to use simulation data way up front for our body and our suspension. Maybe we're going to use a carryover tire and wheel, but we have a completely new body. We've never built any of it. It doesn't exist in the real world yet. We can analyze that or predict what those FRFs would be using simulation tools and then virtually assemble those two components. One of the questions people often ask is, does this work? Well, this is a little bite-sized piece of this study done by Goodyear. It was published in the Journal of Sound and Vibration in 2022, and it was performed in cooperation with Siemens, but essentially you see the tire and wheel combination over here on the left. This is the independent characterization of this source component. And then over here, you notice there's no tire or wheel here. We're characterizing this body and suspension, again, independently, and then virtually putting these two things together. This invariant source characterization of the tire and wheel, these are these things called blocked forces, where we can calculate them either on a test bench or on a vehicle. We have multiple techniques. We're not going to talk too much about that today. But the idea of a invariant force or a blocked force is that it's the same. It's an inherent characteristic of the component itself. It does not matter what you're hooking it up to or how you're installing it. It is its inherent source capability. Okay, so you notice the red and the blue, very good agreement, whether we're measuring or calculating the block forces from a bench level test or all the way up at a vehicle, we get very good agreement supporting this idea that the force is truly invariant. It's not reliant on the structure that it's mounted to. So if we use that invariant source characterization and we build it up into a full virtual prototype, and we make a prediction about using this tire and wheel combination on this independently characterized suspension and body, what will the driver's ear microphone noise be if we drive this down the road? And you see measured versus predicted. So we did this study on an existing vehicle so we could measure the actual response and get our, air quotes, trusted real world answer. And that's the red line. And the black line is the prediction of a virtually assembled vehicle. We see, again, very good agreement between the prediction and the real world measurement, supporting the idea that we can independently characterize these sources and receivers and then virtually put them together. So what does that allow us to do? Well, on a larger scale, it allows us to, as an organization or an industry, independently model a huge library of different components, different bodies, different axles, different mounts, different wheel and tire combinations. These can come from test data that we have. We can make measurements in the real world. We can do this. We can also do simulation. The virtual prototype assembly process does not care where the data comes from, be it test or simulation. So we model all of these components. We model them in a consistent, uniform way in terms of the degree of freedom naming and direction naming and that sort of thing. And that allows us to put them all in a standardized component library where now we go to this shared database and we can say, okay, I want to take vehicle body A, put suspension 2 on it and tire and wheel combination X, and then make predictions. And I can plug and play these different components. And up front, again, not needing any physical hardware, this could all be done with simulation data. I could see for this given body design, what type of suspension architecture or what types of wheels are we going to want to stay away from because they create a problem for us. And so we put them together in this virtual prototype assembly, and it allows us to do several different things. We're going to talk about a couple of these today. The first is contribution analysis, where we can get a very in-depth look at where is the energy coming from, what is the response, what if we changed this component in this way, how does that compare to our baseline condition, and we can boil that down to a very discrete level of information in this contribution analysis. The other thing we're going to talk about today is this NVH synthesis and simulation, and the state of the art as far as Test Lab goes and what's available in Test Lab in 2406 to actually take this virtually assembled machine or vehicle and be able to listen to it and put it through a certain test scenario and hear what it will sound like when we build it. So we're going to take these components, assemble them, but then we can start to play these games like where can we reduce weight with minimal impact on our road noise performance? How much weight can we remove from the body or from this subframe? What tire and wheel combination do we want to put to give ourselves the best option for road noise performance? What I'm going to show you here is how we can use VPA to answer this first question. We've got a couple different subframe designs. One has been weight modified, or one has had its weight reduced in order to improve economy and range. And we'll see if that has an effect on our driver's ear microphone. So I'll show you that now. This is SimCenter Test Lab Neo VPA Assembler, which is the tab I'm on down here. This is available in either Classic or Neo. I'm going to show you using Neo today. But just so you understand how I got here, I launched a desktop and I went to add-ins and I turned on Virtual Prototype Assembly or VPA Assembler tool. And that will give me this tab down here. And I'll be met with this interface. And what it allows me to do is, you see, I start with this thing we call a body or a receiver. We're using the letter B, kind of short for body, which is typically what we're just calling our final receiver, where the human being or our target is existing. And all the way over here is this TS box, and that stands for test scenario. And a test scenario is the time evolution of what we're going to put this assembly through. So this could be a speed sweep, it could be a torque sweep, it could be an RPM sweep, you name it, vehicle speeds, it doesn't matter. It's just versus time, what's going to be changing and what do we want to put this assembly through. So what I'm going to do is I'm going to connect all the way from here to here using these individual components. For this road noise example, I'm going to just load one just to show you how these can be stored and what a sophisticated assembly can look like. So I've got a library here, and all of the components for this particular investigation are found in this library. That library is where we're keeping all these different components. So I could have different tires, different suspensions, different mounts, different bodies, etc. in this library. I'm going to first pull up the smooth asphalt assembly and show you how we're getting from essentially the test scenario on the right. That's going to produce certain loads. That's these boxes here. And these are individual loads coming from the 4 tire wheels on the vehicle. And so you see front left, front right, rear left, and rear right. So 4 tires, 4 different loads coming from these components. And the loads are always connected to these AC boxes, which stands for active component. This is an active component or a source. These are the time or RPM based loads that are generated by the active component. And then these are connected to these passive components, and you see suspension front left, front right, rear left, and rear right. And then that suspension connects either to a subframe, which is another passive component, right? No forces are being generated in the subframe or the suspension. And these both connect to the body. So where the suspension is connecting right to the body, that's where the strut mounts are connecting directly to the body, or in the rear, there may not be a subframe, and those suspension components are connected directly to our body. However, in the front, you notice our front suspension also connects to the subframe, which before it gets connected to the body. And so this is the real path for the lower front suspension attachments. They go into this subframe before they go into the body. So I've created this assembly. I have different test scenarios I can use to put this assembly through. And so I can just right click and say replace component here. It's going to go look in that library for other test scenarios that I have available in this library. And so you see I've got a speed sweep and then 3 steady state cruise conditions. So these are the time evolution tests that I'm going to run this assembly through. The other change I make here, so not only can I change speeds here, but for a given speed condition, in this case, I'm going to leave it at the 70 km/h cruising condition. And I want to assess smooth road performance versus rough road performance, and then compare that to what if I did this weight modification on the subframe? And what if I took some of the weight out of it, make it a little bit more efficient in terms of range and that sort of thing, so I can select this component and change it to be either the original subframe or the weight modified subframe here. Okay, so I would just select this, say okay, and this component will be updated. All of these other components remain the same, right? The test scenarios stays the same, but I now have a new assembly that I want to calculate and assess, and so I would do that for each of these 3 tests: smooth road, rough road, and then rough road with the weight modified subframe here. So when I do that, in my results section over here, you see I've got 70 kph, smooth baseline, rough baseline, and then rough weight modified. And so what I can do is now I can start to investigate some of the results. And so I'm going to come in here and just say reset all. And so I'm using this DOF ID versus run name versus function, and I've added this column, which is very useful for looking at VPA results. It's this result type, and I did that by saying add a new function, and I just started typing VPA, and I got this result type, which is added here. By default, it would have just been DOF ID, run name, and then my function class. I've added this column here. I'm interested in what's the result at the driver's ear microphone, so I'm not going to say show me all of these. I'm going to scroll down here, and you see how much data we have, right? So it makes it very convenient to just be able to sort through here. So now I'm only looking at the driver's microphone. I have 3 different runs here, and now I can look at the VPA result type, and I can do some very quick assessment. What is the impact to the driver between the smooth baseline? So I take this frequency spectrum here, and I see the multi-load contribution. And so let me increase the size here, but I've got the frequency spectrum of the microphone for this given condition, in this case, smooth road, given the original subframe. Overall RMS here, about 54 dBA. What happens if I take that same design, but I drive on rough road? I can find that same result, but now under this run, I drop it in here. Oh, and we can see across the board, as we'd expect, the noise levels go up across the frequency spectrum. Again, this is to be expected. So we go up, I don't know, 9 dB or so. Now let's see what happens if we do the weight modification on that subframe. Is that really going to screw things up for us? We can add that same multi-load contribution spectrum. And we do see the noise gets indeed worse, but one of the things that sticks out is this peak over here. And we want to know, okay, this didn't exist before. Where is this coming from? What components might be responsible for this tone sticking up so badly where it wasn't before? This is from the 70 kph rough weight modified test. And so I'm going to go over to that simulation or that virtual prototype assembly, and I'm going to look at the component results now. So where I was looking at all results from all 3 assemblies, I'm going to drill into just some component results just for the one. So I select this, and this table gets reduced to just the results in this single folder. So I can create a function display here, and I can grab the spectrum load contribution for this assembly. And so what is this? What are these 4 loads, right? We had 4 tires. Those are the 4 sources for our load. What this result is showing that at the driver's ear, here's the contribution from the front right, the front left, the rear right, and the rear left tires. And if I go back here and say, what frequency was that at? Okay, it's about 380 hertz. I'm guessing that's right at this big red line, and it is. So we can see right off the bat, without doing anything but loading our 4 loads, we see that the front tires are responsible for that tone. This makes sense, right? Because in our assembly, only the front tires are connected in any way to that subframe. The rear aren't being weight modified because they're not connected to that subframe in the front. So let's go one level deeper and say, okay, we know it's the front tires, but let's take a look at all of the paths coming through those front tires. And so we see all the different directions and rotations for all 4 tires, and we start to see that 380 hertz peak here. These are all the possible directions and rotations from all of these different hub centers for our 4 tires. And let's start figuring out which directions of our front tires. So if I go double cursor here, add a sorting range. So now it will sort based on what's in these cursors here. And I right click over here and I change sorting to RMS. So now it'll look at the RMS between those cursors. And if I make this a little bit more narrow, move it over to this 380 region, I don't need to look at all of these guys down here, right? I really just want to know what are maybe the top 10 hitters. So I'll say view, show me the top 10. And as it's no surprise, these are front left, front right, front left, front right, right? There's no rear tires here in the top 10. But now what I can see is it's more information or another level of specificity on what about the front tires is causing this tonal issue. And I see it's the front left, the center of the wheel, and the X rotation. So rotation about that point around the X axis. Second is the rotational around the Z. Okay, so the RY is the rolling axis, and we don't bother with this because that's sort of a free rotation. And so this is rotation around the other 2 directions, both toe and camber. Essentially those 2 rotations, and then the X direction, and then rotation in the Z, et cetera, et cetera. So this gives me a very high level of information. And you notice front left, it's rotation in the X, front right, it's rotation in the Z. So different sides have different effects. Maybe that weight modification, the subframe design may not be perfectly symmetrical between left and right, and so that weight modification might be affecting the 2 sides a little bit differently. So this is really just to give you an idea of what kind of contribution analysis you can do given a virtually assembled component or series of components that are put together virtually. Using CAE data, any test data that you'd have available. You can put these things together and then start playing what if scenarios and see what is the difference. What will this cause me a problem if I do this? Would I be better off with a better, different subframe? This might prompt me to say, okay, we can't do a weight modification, at least in the manner that we did it without causing a huge tonal problem. What if we saved weight in a different manner in that subframe or went with a slightly different subframe design? Maybe I go back and I simulate something a little bit different. All of that can happen very, very quickly, whereas in hardware, we'd have to literally manufacture it and change the tools and all of that. That takes a lot of time and money. So that's the whole point. So that's VPA and contribution analysis. The other thing we can do with a virtually assembled prototype is this synthesis idea. So we want to be able to drive or listen to the virtually assembled vehicle or operate the virtually assembled washing machine or boat or whatever it is. And so we start to talk about noise and vibration simulators. And at the high end, at the most sophisticated end, you have this full vehicle simulator where you have two different models running in parallel. You have this performance model, and in the case of an automobile, this is everything to do about the mass of the vehicle, the transmission, the gear ratios, the control algorithms in the automatic transmission. It's everything about the vehicle that we need to know in terms of when I see this RPM and this torque, how fast does it accelerate, etc. That's this model over here. And then you have a whole NVH model that's running in parallel. So you have main noise sources in a vehicle are going to become the road noise that we just looked at. There might be a powertrain, so this is going to be electric motor or cooling pumps or something like that. And then you have just the wind noise of driving the vehicle down the road. Different vehicles are going to have different wind noise performance. And so using these three different sources, we can balance them. And these are also going to be a function of RPM, vehicle speed, torque on the powertrain, etc. We want to take those two models working together and then export or output a audio or a vibration output in the time domain that we can experience and drive ideally in real time. So that's the sophisticated end goal. Where we are right now in Rev 2406 is that we are now able to take VPA results and process them in this NVH simulator in an offline method, which means we have a static time profile in either RPM or speed, so vehicle speed or RPM for a rotating component. And we have our VPA results in the frequency domain. Those are the inputs to this simulator. And so I'm not dynamically driving it. There's no vehicle model involved, but this is really just the first step to say, okay, I've got this VPA. I do that road noise, virtual prototype assembly assessment that we just looked at. And now I want to say, okay, what does that really sound like? I see that 380 Hertz peak, but what does that sound like? And do I really care? I'd like to hear all three of those vehicles maybe. So I have my VPA results. I have some profile in the time domain, which at this point can either be RPM or speed. And I generate this NVH model in the new NVH simulator. And we process those two input pieces and we output an LDSF file. And so with the LDSF file, that's the SimCenter time domain format. We can listen to that. We can do all of the cool audio replay and filtering stuff we are accustomed to in TestLab Neo. We can see live spectrums, play what-if games with filters, calculate sound quality metrics. It's literally a driver's ear microphone recording on a vehicle that or a component that you don't actually have yet. You virtually assembled it, but all this stuff you would typically do with that driver's ear microphone recording, you can now do with the output of this NVH simulator. Oralization, audio replay and filtering, sound quality metrics, etc. So that's what is available in this offline NVH simulator. This is what it looks like. And I'll take you through all the different components here. So just showing you some of what I'm going to show you in the GUI. In the simulator tab in the ribbon, we create a new simulator that is just like that NVH model. It's the combination of our VPA results and our scenarios, or our profiles rather. That's our RPM or vehicle speed right now. So we activate a simulator. We add a component, and these components are active components where loads are coming from or acting on. And then we can add a profile, and these will be either RPM or speed blocks in the time domain. Once we create that component, it's going to look in our active section for some VPA results, and it's going to limit our options here to the things that it finds in these VPA results. And I'll show you this. It'll become a lot more clear. This is just sort of a nice reference after the fact. But you start with a component, you'll select the available loads, the result runs that you have available in those VPA results. So this could be smooth, asphalt, rough road asphalt, and then weight modified rough road, the group contribution, and then what do you want to see the target LDSF being, 1 microphone, 2 microphones, etc. And then your profile, again, it's going to look in this case in the input basket. So this does not need to be one of the test scenarios that you have used to provide or build the VPA results. You can have these profiles exterior, and you can run different types of profiles for all of your different virtually assembled products. And in this case, you put whatever you want to use for time domain in the input basket. It finds that, and then you select the channels accordingly. The profile is, again, this RPM or vehicle speed. The component is either going to be a spectrum or an order, depending on the kind of active component it is. And so these are either going to be a single spectrum or waterfall input for the active component, or it's going to be a rotating component like an electric motor. I'm going to show you this where we have orders in there as opposed to broadband noise. In the project tree on the left, you'll see your simulators show up in a new folder called, aptly named, NVH simulators, and then each simulator will have components underneath it. And so in this case, we had 3 different components. We had wheels, then structure-borne from the EDU and airborne from the EDU, and we had 2 different profiles that we were putting this assembly through. The results will end up as runs in the active section, and the results will be the time domain results for your target. So in this example, we're producing a time domain synthesis at the driver's left and right ear, and we get this LDSF out versus our vehicle speed and RPM, just like we would expect. So let me show you what this looks like. And just to show you what this looks like in terms of add-ins, if you have installed 2406, you may have seen this, but it's only available in TestLab Neo. If you open TestLab Desktop Classic, go to add-ins, you are not going to find it. It's only available in Neo. Sort of makes sense because that allows us to take advantage of all the Neo audio replay and online filtering capabilities that are really nice in TestLab Neo. So you see simulator offline, you can load this up, it's 90 tokens, and you'll get this tab down here. So as I mentioned before, it's going to look in your active section. In this case, I'm going to look in this virtual assembly results for the results of my VPA. But in this case, I'm going to build this for you just so you can see how this process works. And then I'll show you a calculation here in the VPA assembler. In this case, I've got an airborne noise problem with an electric drive unit in an electric vehicle. And so for my body, I'm going to right click and I'm going to assign, and I see I've got this different libraries. Previous, I was using that road noise library. Here, I'm using one specific for the EDU. I've got a couple different body designs I want to assess here. And so I assign body 1, airborne component. So this body receiver, what this box is really just a set of FRFs that I have acquired, either in the test world or I have simulated. But essentially, I have a response at the left ear and the right ear in the passenger cabin. Those are the responses, and I have 5 different inputs from the EDU, airborne, the back, the front, the left, the right, and the bottom of the electric drive unit. So I have 5, technically 10 FRFs here. They're P over Qs, where I've set a Q source at each of these EDU locations that I've measured the pressure response inside this body, or I simulated those same scenarios. But that's what this body is just a collection of those transfer functions. Next, I'm going to load a direct load in this case. Because airborne do not go through passive components, it's sort of a restricted version of the active component where it's not a mechanical force acting on some component. The active component in this case is the EDU, and that acts directly through the air on the body. And so we have this thing called a direct load. And because I've taken care, I can select these two and I can say auto connect. If I did want to do this manually, I would just see a list of input degrees of freedom available for the body receiver over here. In this case, there are these EDU, 5 EDU locations where we put the Q source and measured. And on the active component side, we have, this is the actual direct load of the force. And so you have an acoustic force or volume acceleration over here. I was able to automatically connect these because I was very careful in naming these. And so the software knew, oh, EDU, airborne, right, comma S, matches up with this guy, left to left, etc. If these were slightly different named, I could connect them manually, no problem. Similarly, I'm going to assign a test scenario. In this case, I'm doing an RPM and a torque sweep. And so now that's specified, and I can come in here and I'll say connect these components. And you see I have a rotational speed over here, and I've got a rotational speed over here. So right now I'm not going to use this torque. I'm going to use the rotational speed. And now I've got this virtually assembled assembly, for lack of a better term. Here I'm going to say, okay, I've got body 1 with this torque. So I'm going to say this is body 1, whoops, airborne baseline. I add that to my assemblies. Now I want to say, okay, what happens if I change that and I replace that body with maybe this second body, body 2, so it's a different design. And this one, I'm getting these FRFs from CAE, or the simulation department. So these are not FRFs that I've measured, but these are just ones that I've had simulated. They're thinking about making these changes to the body. Our CAE team made these FRF simulations and provided them to me. And so now I'll call this body 2, airborne baseline. I add that to my assemblies, and you see it says ready for processing. And then this third one is defining. And so I'm going to replace this one more time. And someone said, well, what happens, how much is the trim really doing for us? So they created another simulation where we had the second body model, and they pulled out all of the acoustic trim. So all the carpet, headliner, front dash, all of that stuff is removed. And we'll see what is going to happen there. And so we say no trim. We add that to our assembly, and now I've got these 3 assemblies ready for processing, and all I have to do is hit run here, and it's going to batch process all 3 of these assemblies and run them all through this RPM sweep and produce 3 different virtual prototype assembly results. And so now I've got these results over here in my active section, and I can look at all of those results here. And I can do the same contribution analysis as I did before. Let me remove all of those. And I'm going to change this and just sort on body 1, EDU, body 2, trim EDU, and body 2, no trim. So we have our 3 results here. We've got body 1, body 2, and then body 2, no trim. If we look at, in this case, total contribution, there is body 1, body 2 with trim. We see it gets louder. Body 2 with no trim, and we see it gets significantly louder. We certainly have these type of results like we looked at with the road noise example, where we can look at all of these different contributions and we can make an assessment in terms of decibels versus RPM. How much worse is the second body, and then second body with no trim from where we started. The next step is to use this NVH simulator. And again, this is offline, so we're using VPA results and static profiles. And it's going to look in the active section. So I'm going to look in my virtual assembly results section. I'll expand this so we can see, but I'll create a new simulator. We'll call this simulator 1. That's fine with me. And now we need to add some components. In this case, we look in the active section. We see we have airborne and structure-borne. I didn't do a structure-borne assessment right now, so I'm going to look at these airborne active components. The loads associated with that airborne are obviously the airborne loads. And now we see our different results in here. And I'll add this body 1 EDU airborne. And I can do left and right ear. In this case, I'm just going to do the left ear so we don't get a bunch extra results, but I could do left and right ear and then listen to them together. And that will become a data source here. And we see this is an order-based assessment or component. It's got order 6, 12, and 24 for this EDU. But I've got 3 different bodies, and I want to add all 3 of these components, and I want to be able to synthesize all 3 and see how they differ. And so I'm going to look at those same loads for body 2, trim EDU, do the left microphone, and then one more, I've got the no trim, body 2, no trim. Okay, so I've got 3 different sources. Those are my active components. Now I need to create or bring in this profile. And so the profile is going to look in the input basket. And so I'm going to look in my input basket here. So I'm going to take that RPM sweep and I'm going to replace that in my input basket from, again, this could be an external source that I just have a bunch of different profiles in. In this case, it's a profile I had right in this project. So I say add profile. Currently, this is restricted to looking in the input basket. So you see it's grayed out, but it looks in the input basket and says, is there a vehicle speed or a rotational speed in there that I can use? More dependencies like torque and things like that are coming. In this initial release, we can only use vehicle speed and RPM. So I say rotational speed. In this case, it found 1. So I'm going to pick that guy. And I say, okay. And I can say auto arrange, so it makes a little bit more sense. So this profile of rotational speed sweep is going to go through each of these different virtually assembled components or virtual assemblies. And if I ran it like this, what I'm going to synthesize or my result will be as if I ran through all 3 bodies at the same time. And so I don't really want that, right? I want to do one at a time. And so I can come in here and I'm going to say, I just really want to take this RPM sweep and go through body 1 first. And I can come down here and say, this is body 1 synthesized, okay? And I run that. It takes that data, it runs the synthesis through that virtual prototype assembly, and now I've got a new result in my active section called B1 synth. Now I want to say, all right, I'm going to turn that body off. I'm going to do this guy. And we'll see this is body 2 synthesized. And so I run that, takes that same rotational speed sweep and puts it through that second assembly and all those results that we looked at just a minute ago. Okay, that guy's done. Now I can switch this guy off, turn this guy on. This is body 2, no trim synth. And I can run this last one. So it's taking that RPM sweep, synthesizing it through that third assembly. And now I've got 3 different LDSFs. I can now do some more traditional NVH work on these 3 different virtual assemblies. So now I'm going to come in here and on this same level, I'm going to reset all these filters. In terms of DOF ID, I don't want all, I just want the microphone. And the run name, again, don't want all, I just want B1, B2, and B2 no trim. Boom. And so now I've got 3 time domain LDSFs. Okay, so if I look in here, you see I've got an LDSF for each of these that I can listen to. It's time domain, and so I can do anything I would be able to do on a measured microphone. Okay, but for this example, I'm going to look at all 3, and I've got body 1 is up here, body 2 is down here in the blue, and then body 2 with no trim is here in the middle. And being in Neo, I can take these and I can start replaying these, but I can quickly listen back and forth to these 3. I can do things like look at the spectrum map for these. Okay. And so I can look at body 1, body 2, or body 3, no trim. And if I look at the color scale here, I can see body 1 limits, make that free, 57, I'll lock those there. So now if I switch to body 2 with no trim, you see the levels, I see a lot more red here in my overall. I can do a domain order stop filter to see what it would sound like if I wanted to. Let's see, I can do this dynamically, and I can go filter this order out. Instead of looking at the spectrum map, I can look at it live as well, and I can see, if I zoom in down here, the filtered versus the non-filtered here. As I turn that filter on and off, I can hear that in real time. I can hear a difference as I turn that filter on and off. I can do some very quick assessments on how big a deal is this no trim in our second body. I can calculate sound quality metrics because I've got 3 different LDSFs here that I can process in the traditional way. Okay, so that is the functionality of the new NVH simulator available in 2406 in and offline mode. This is an exciting first step where we're able to oralize immediately after I do a virtual assembly. I can now oralize that with almost no additional work by turning on the simulator, running it through some established speed or RPM sweeps or different operating conditions, and then hear what those assemblies sound like, do some traditional sound quality analysis on them, etc. So stay tuned, but very cool new feature of 2406. And that's all I got.
Perfect. Well, we just had a question come in. Someone asks if the offline simulator runs on tokens.
It does. It is 90 tokens.
Awesome.
Yeah.
But thank you, Scott. I don't see anything else on the chat.
Great. Well, thanks, everybody. Appreciate you tuning in.
Thanks, everyone.